Our last conic section we're going to look at is called the hyperbola. And this is going to be the set of all points in a plane such that the absolute value of the difference of the distance from two fixed points called our foci is going to be constant. We're going to see that we're going to have a lot of similar features and attributes to the hyperbola as we do the ellipse, just with some notable key differences. What I want you to notice first is that we have this major difference between the two, between the ellipse and the hyperbola, where the hyperbola is a subtraction equation. And A is always going to be located in the first term. The difference is the direction that the hyperbola opens will determine whether or not x is first or y is first. So if x is first, we have a parabola that opens along the horizontal axis. But when y is first, we have a hyperbola that opens along the vertical axis. H and K still represent our center. A still represents the distance from center to vertex, and so we see that distance represented in our diagram. We have the distance from center to vertex here. That's our A value, and it's A going this direction as well. So 2A spans the distance from vertex to vertex, giving us what's called the transverse axis. Now, we don't use the same nomenclature as we did with the ellipse, instead calling it a transverse axis instead of a major axis, because it's not always going to be the largest. It plays the same role as the major axis, but again, A does not have to be the largest. We'll say it does not have to be largest. And so when we're comparing ellipses and hyperbolas, with ellipses, we care about which denominator is bigger so that we can identify the major axis. Here, we care more about which denominator comes first for the transverse axis. And the reason that we care about position with the hyperbola is because subtraction is not commutative. Which number comes first makes a difference. But when adding on the ellipse, addition is commutative. The order doesn't matter. So which denominator is first is irrelevant, but the size of the denominator tells us which one is the major axis being the largest. A is always going to be part of our transverse axis, and A will always be first on the hyperbola. So it's a key difference between the two to note. Now B gives us the length of this conjugate axis. And so going in the perpendicular direction from the vertex up or down, perpendicular to the transverse axis, we have this length of B in both directions. Now, it doesn't go to a specific point, but instead, A and B combine to give us this boundary box. And this is an imaginary box that's not actually part of our graph, but this forms what we call a fundamental rectangle. And the fundamental rectangle is very easy for helping us identify and to draw the asymptotes of our hyperbolas, because our parabolas on each side will extend out in a certain direction, but to determine how wide it's going to be is based on asymptotes that pass through the center, but they also pass through the corners of this fundamental rectangle. And so using this rectangle, we can write the equation for our asymptotes. If I have a line that runs through here and is centered at the center of my hyperbola, and the slope of that line is the length of B over the length of A, then I can write an equation where I have B over A times x minus h plus k. So we're still using this value for center, and we use that fundamental rectangle to determine the slope, either B over A or the slope A over B. Now here I have a typo with our Pythagorean relation, so let's fix that. Instead, unlike our ellipse, it's actually exactly the same as our Pythagorean theorem, a squared plus b squared equals c squared. Again, C still measures the distance from center to foci, but unlike the ellipse, the foci are actually further out. Our foci are further out than our vertices, so C has to be larger than A. C will always be larger than A, and C will always be larger than B. So we'll use our Pythagorean theorem where the sum of the two smaller distances squared equals the square of the third distance. So we'll start by graphing our hyperbolas, see some of the similarities between the ellipses and hyperbolas, and then we'll go and look more closely at some of the key features. Now, just like with everything else that we've done so far, in order to graph, we need to start with the center. Well, since there's no h value here and no k value here, we know that they're going to be 0. So our centers are going to be at the origin 0, 0. And then, in order to graph, we're going to need the values of a, b, and let's also just find c so we can get a perspective for what that focus is going to do. So a and b, these are used to build the fundamental rectangle that we use for our asymptotes. A also gives us our vertices. So the first value is always a squared, and the second one is b squared. So a is 9 and b is 8. Now we need to consider what direction our parabola or hyperbola is going to open. Since x is first, it's going to be along the vertical axis. We'll have our center, and then our vertices will be to the left and to the right, and a units, which is 9, to the left and the right. So if our center's at 0, 0, we'll have a vertex at 9, 0 and negative 9, 0. Let's go ahead and plot those points on our graph. Center at 0, 0, vertex, and vertex. Now, we're going to use our fundamental rectangle. That's where our b value comes in. So perpendicular to our a value, we'll have our distance of b, 8 units above and 8 units below. But the b value doesn't go to a particular point, but instead tells us how far up to go to build this imaginary fundamental rectangle that goes around and also passes through the vertices. And so what's important is to know where these corners are, because through these corners we'll have to draw our asymptotes. Those asymptotes will tell us how wide our hyperbola is going to be. And so if we take our graph here, we're going to use a dotted line to represent our fundamental rectangle. So through the vertices, draw a little bit straighter than that. Oops, that's too low. It would be a negative 8. Here we go. And so we just want to connect all of these together to get this imaginary rectangle. And then through the corners of the imaginary rectangle, this corner down here, from here to here, we want to draw a dotted line that goes through these corners and extends beyond in both directions. These are our asymptotes. Same thing with this corner and this corner. And then from there, we actually have enough to draw our hyperbola. We know where the asymptotes are. So our hyperbola is going to start closer to the asymptotes, but slowly get further away as it approaches the vertex, pass through the vertex, and then start to get closer and closer to the asymptote, but it will never cross over the asymptote as we zoom out. And we'll do the same on this side. We'll start close to the asymptote. We'll come down, we'll get to the vertex. I don't want it to draw a straight line for me. The vertex, pass through the vertex, and then come back and approach the asymptote. And there's our hyperbola. We've graphed it using the asymptotes with the fundamental rectangle, our vertices, and our center. So we've been able to identify our vertices as 9, 0 and negative 9, 0, as well as our center. Now we can also find our foci. We don't need them to graph, but it's a good idea to understand where they're going to be located. We use a squared plus b squared equals c squared. 81 plus 64 equals c squared. So we get 145 for c squared. So c is going to be approximately 12, just above 12. It's 144 is 12 when we square root it. So 145 is just a little bit more. So we know our foci are going to be located at approximately negative 12, 0 and 12, 0 because they're going to be past the vertices. We'll have a focus and another focus past the vertices in both directions. Here's a focus and here's a focus. And then if we want to talk about the asymptotes, then we want to consider our equations. We have a linear equation, but we need a slope. So we're going to think about our slope of this line. So considering this line that's going through here, we want to think about the rise over the run. Well, the rise of this slope is equal to the b value in our fundamental rectangle, and the run is equal to the a value in our fundamental rectangle. So our slope is going to be positive and negative b over a. It's the same for this line here, except it's going down b and right left, or right a. So it's the same slope, and then it's centered at h and k. So we're going to be using this formula for our slope and our center. Since our slope is 8 over 9 and our center is at the origin 0, 0, our equations for our asymptotes are given with positive and negative 8 over 9 times x. So we don't need to graph these equations precisely because we've got them by using the fundamental rectangle, but you will need to be able to identify the equation for the asymptotes. Let's go ahead and do the second graph. So same thing, we'll start with the center, and this is also at the origin, but notice how y squared is first. That means it's going to be a vertical axis opening on the hyperbola. Now a is always first. A squared is 4, meaning a is 2. B squared is 25, meaning b is 5. Notice how a is not larger. That's why we don't call it a major axis. It's the transverse axis. So we have our center, and then our vertices are going to be above and below our center, a distance of 2 units. So we'll start with that. We have our center, we have a vertex, we have another vertex. Now again, we need to use our fundamental rectangle to figure out how wide our hyperbola is going to open. We need to figure out how far to the left and right that rectangle needs to go. Well, our b value is 5. So our rectangle will extend out 5 units to the left and 5 units to the right. And we'll form a box with perpendicular lines going through the vertices. And our asymptotes will pass through these corners. So we can draw our asymptotes from corner to corner and extend, corner to corner and extend. And so now that we know where our asymptotes are going, we know exactly how wide our hyperbola is going to be. So let's go ahead and graph it. So again, we start closer to the asymptotes and then approach and cross the vertex, then come back up and approach the asymptotes again. And we do the same in the other direction. And now these sketches aren't perfect, but they get the idea across of generally how wide it's going to be, how far apart the vertices are, and they give us enough information about the general shape of our hyperbola. If we wanted to, we could find C to plot the foci. We don't need to in order to graph. We just need A and B to draw the graph. So unless the foci is asked for, you don't need to calculate C. Now here I went ahead and I graphed on Desmos all those features so we can kind of see. We've got our fundamental rectangle in blue. This is not part of the graph visually, but it's helpful to identify it and kind of understand what its relationship with the asymptotes are. We see it passing through the corners, and it's forming this bounding box, and this distance from here to here was A number of units, and from here to here was B number of units. We also have our focus just past 12 on both of these. And so the red line, that is the graph of our hyperbola in its entirety, but the box here helps us when we want to draw it. Notice how the gap between the parabola on each side and the asymptote grows as we get closer to the vertex and shrinks as we move further and further away because our line is approaching the asymptote infinitely. With our second one, we see we have a much wider hyperbola with our foci above and below 5 and -5. We have this wider fundamental rectangle that we found, so this B value of 5 and this A value. Here, if we did want to calculate the asymptotes, we would note that the slope in this case is going to be A over B because the rise is A and the run is B, and then we could use the center for the rest of our equation. So we could quickly identify this is 2 over 5 x with our center located at 0, 0 for the two asymptotes that are given. Next, we'll go ahead and we'll look at some of the features of the hyperbolas from the equations.